law dealt with the concentration relative to that rate of the reactant. Then we correlated that to get the integrated rate law, where now we're also looking at the time and the concentration associated with the speed of that reaction, right? And up to this point, we've looked at, in terms of the integrated rate law, only the first, right? The first order, and that's where we left off, I think on Tuesday, was it Tuesday, Thursday? So on Tuesday, that's where we left off. So then we did a couple problems. Here's the third problem in that context. Hopefully that kind of wraps up to see the relevance of this and what we've done and where we're going with it. So we've done the first rate law, the first integrated rate law. We're going to get into the second one just after, but I think we have one example left before we move into the second one. So here, radioactive decay of U-238 is first order. So I'm telling you here it's first order. If you didn't know that, then we're going to look at a couple ways to figure that out. Okay, 17. But for now, you kind of know one way if you looked at the rate law, but not necessarily with the integrated rate law, and we'll talk about how to figure that out through graphing. So this first order with a half-life of 4.5 times 10 to the 9th years, that's pretty long, right? So that means that that's going to sit around for a long time. That's radioactive uranium, right? So I don't think you want to be exposed to that. You also need to know how to protect yourself from that. Different radioactive isotopes, you would protect yourself with different things, and thicknesses of those things, etc. So anyways, you have this half-life. How long would it take for 10% of U-238 atoms in a sample of U-238 to decay? Very first thing that you should be thinking about, and I think I brought this up either Tuesday or Thursday last week, or both. In most of these problems that you're going to do in this class, when you read this, what should you think about? Very first thing, without even reading this, what should you already be thinking about?
Thinking about rate?
What's the chemical reaction that's occurring?
Right.
What's happening? So it's a decomposition. So you're basically going to be looking at something. Let's just say U-238 is going to go to something else. Let's say this is U, what is it, 238? Let's say it goes to 237 plus one of those, one electron. Okay. You kind of want to have a sense of what's going on always, especially in this class. And that's going to be huge to determining things. So I'm looking kind of like, you could just call this a decomposition. It's not a traditional style reaction, right? Where you have, you're dealing with an electron here. But that's what I'm looking at. So therefore, I'm saying this is first order. First order, I'm always looking at what? Reactants?
Yeah. Right.
Okay. When I deal with rate laws, and so this is first order, so then what would the rate of this thing be?
Going down.
Rate would equal?
K.
K, yes. U-238. Power 1, because it's first order. Right? I already know this much. Okay. What else do I know? I know the integrated rate law. Okay, and do I know the half-life as a relationship to that integrated rate law?
Yeah.
What is it? So the half-life, which is T 1/2, is equal to what?
4.5.
Yeah, 4.5.
What? No. Not forget this problem. What is it? What's the half-life of a first order? Is it negative?
Oh, the 6.
693. Over. Is it?
Over K?
Mhm.
Is that what it is?
I don't think it's negative.
Not negative? Is this what it is? You guys should know this, right?
Yeah.
Okay, so I do know that the half-life is what? It tells me 4.5 times 10 to the 9th years, right? So can I figure out anything from any of this information here?
You can
Figure out the K.
I could figure out what K is, absolutely.
What your constant, yeah.
If I figure out what K is, I could probably do something with this, or I could use the integrated rate law. What was that for first order?
integrated rate law is K equals
log of, in this case, U238 at what time? Over the log of U238 initially, right?
Yeah.
Right.
Equals K, negative K, T. Is that it?
Mm-hmm. Negative KT, yeah.
Okay, now we're getting somewhere, right? So, and what do I want to know here? How long would it take for 10% of these things? So then, this here is the initial. This is going to be what?
Final.
Yeah.
The final, yes, but what is it going to be? If I know that I want 10% of the initial.
90% of that.
It'd be
10% might be.
Yes, somebody over there is saying it right, but I'm going to wait because I think there's some are still not seeing what I'm getting at here. If I want to know how long would it take for 10% of them to go, then what should be here at this time? 10%?
90.
90%.
Right, what's remaining?
Yes. Somebody said it right back there, so you're absolutely right. Okay.
Right.
I recognize that, but I knew that there were some other things going on that I wanted to postpone that. So this should be 90%. So I just make it 1 and 0.9
Right.
for each of those. Okay. I could solve for K here, and I could plug in K, and ultimately, what did I want to know?
Time.
How long would it take?
Yeah.
So that's what I'd be solving for. So I took all the things that I knew,
Nice.
which you guys currently know, and said, how do I solve this problem? Very first thing, though, is I wanted to identify what is it? What kind of reaction, or what am I looking at? What am I starting with? Okay. So let's see. Hopefully we did it right. Step 1, use the half-life data to calculate K. That's great. Okay, that's what we did here.
Yeah.
Because we knew
Electrons.
we know this, so we could solve for the K. Step 2, what do we use the integrated rate law to calculate for time, for decay, because I knew I had these two things here, I had this, now I can solve for the time. Could I have done it here? I could have solved for the rate here, but the rate wouldn't have given me any information about the time, so that's why I can remember the rate law, which is what that was, is the concentration relative to the rate. The integrated rate law incorporates what else? The time, absolutely, okay? So I recognize, make the correlations, then it becomes relatively easy. I could have used anything here, 1.9 or any ratio that way. It's just easier to make something 1 and then, right, 0.9 is 90% of it. You could use whatever you want there. Okay, so let's see. Okay, there we go. And remember, make sure your units there, that's year. So remember in the past we looked at seconds, right? In this case, does this matter? Do I have any, is there any reason to change the year there?
No.
Not yet. There could be later, maybe not, but at least at this point, it doesn't really matter what it's in, right?
Yeah.
I could change it, but it wouldn't give you any advantage, at least at this point. Okay. So there's my K. Is the K going to change?
No.
It's constant. Assuming what?
Assuming that
Temperature is the
that's
same.
Thank you. Assuming that everything stays the same, the big component of that would be temperature. And we'll see that in a little bit, absolutely. So if I change the temperature, the K could change. Okay. Step 2. Oh, look, the integrated rate law, and A, let's make A1. Okay, good. And then A at some time is 0.9. Once again, what's the common mistake if you got to this point? You're going to put 0.1, not 0.9, because it told you 10%. But if you take at 10%, that means that you have 90% left. Because if you look at this here, you would say, okay, if I lose 10% of this, what do I have left? If you just try to play the little game in your head, you might not see it that clearly, and you might just say, okay, 0.1 instead of 0.9, right? Okay, so make sure that's clear. And we have K. Okay, good. So now we can just plug and chug. 0.9 over 1, I can just do this in my calculator. I get this here. I divide whatever I get here by this, and I get my time. And it's still in years. Does it matter?
No.
No. So in this case, I didn't need to make any adjustment. Right? There was nothing that I was canceling out, so the time in years is perfectly appropriate. It didn't ask for anything else. But this gives you some insight in how to solve equations related. If you know enough information here, if you could figure out these kinds of things and then translate them to the question, then you can solve for all kinds of things. And why would I want to know that? Well, maybe because I'm going to say at 10%, when I have only 90% of this, because I have a certain amount of it, when I have 90%, I could then now take it and move it to a better location where nobody will be affected by it, right? Because it's radioactive. But at the amount I currently have, it's too much. I don't have anything that I could move it in some kind of a truck that wouldn't affect maybe the truck driver, and anywhere I'm going as I drive through to whatever location for storage that I'm going to find. Right? So there could be a reason why you'd want to know when it has 10% less of that radioactivity. Because that's exactly what I'm saying here. This actually becomes non-radioactive based on this time frame. This is the amount of it that becomes non-radioactive. Right? Is that okay? Everybody see how this works? Okay, good. Okay, so now we'll finish off the first order, at least, integrated rate law by looking at graphing these. Because in the graphs, you can gain a lot of information. Okay, and let's just take a look. Here's my equation for the integrated rate law. I'm going to rearrange that, which I'm not going to hold you responsible for. You just have to know what the rearrangement is. And what I'm going to do is I'm going to put it in the context of a linear straight line. Y equals mx plus b. All of you know that kind of equation. I just have to line it up appropriately so that when I make that graph, it's going to be linear, either positive slope or negative slope, based on whatever I'm defining as my y and my x. Okay, so let's take a look. So I split this out. By the way, just to remind you, if I have something like this, this becomes log of this minus log of that. Okay, then I move this one over to this side, that's where I get the positive. And that's how I have it separated, no big deal. Not that you need to know that or whatever, but just in case you want to see how that came across. What does this look like? Y equals m times x plus b. What's b? The y-intercept, right? So this is my slope. This is my x. This is my y. So when I have the integrated rate law of a first order reaction, which we looked at how to get this here, then I convert it into this here. I now have my setup of y equals mx plus b. Okay. There's my y. There's my m. There's my b. T is x. Now I could plot data, right? I needed data to determine that this was a first order to begin with. I can now plot that data in this format. Don't get confused though, look at what I'm plotting. I'm plotting the log, natural log, of the concentration of, in this case, A, at some time, 2T. So that does mean though, that if I try to figure out what let's say the concentration of T is, I can't necessarily just go right to this spot and find this because I'm finding the log of it. Then I have to take the inverse log of that in order to get the actual concentration. So keep that in mind. Also, when I plot it, I can't just plot this. I have to plot it with the log to get this linear curve. Okay, so let's take a look. So everything on here is pretty much what I said, except for I'm now going to apply this equation here into that. And one thing I should point out, the slope should be negative. So should it go up this way or down this way? Down, right? Okay. So here's some data. So here's my, based on this equation here, okay? So I'm looking at this piece here. So at some time, 0, 100-second intervals, 700, 800 down to 15. I start with 0.1 molar of the SO2Cl2, and over each 100-time interval, 100-second interval, I get a reduced number for the molarity. Okay, just a set of data. I translate that data from here on to here. Now, what do I have to do with the molarity here is I have to what? I have to take the natural log of it. So this is the natural log. That's why these numbers are not the same. This is the natural log. That's my y. Here's my time on the x. So I can correlate the time from that last chart directly at 100, 200, 300, 400, 500, etc. And then each one of those points would be the log of that concentration given that you had in the prior thing. So now from this, of course on an Excel graph, it's always nice because it gives you this, right? But if you have to figure it out, or if it's given, you have something like this, what's your slope? Negative 0.000290, right? What does that also mean?
That's a
You can solve k that way, right? So you can solve k from this. You can solve at any point, at any time point, what concentration you have with the natural log, and then you could adjust the natural log, right, by taking the inverse of it, and you could now solve for the concentration at any time with this equation. What do I automatically know? If I saw this, what could I tell you about the actual rate associated with this?
You know it's first order.
Mm-hmm. You know it's first order. This automatically tells you it's a first order reaction, right? Because it's a straight line with a negative slope. Because it's given in this format, log of this first time. That automatically means it's a first order. If it's not a straight line, would it be a first order? No. So it's a way to quickly evaluate a graph and determine, is this a first order or not? You don't know anything else, you just know it's not a first order or is a first order at this point.
So for the first order in the line, like it has to be straight. But
Straight
it can
line.
be increasing or decreasing.
What do you mean by increasing or decreasing?
So it doesn't matter if the graph goes down.
It does matter. Absolutely matters.
Oh, because it has to be negative.
Based off of the first order integrated rate law, we solve for this, which means that if it's a straight line with the log of the concentration relative to the time, then the slope will be negative and it will be a straight line, which is exactly what we see here.
So we only
Okay,
use
all
the
this has
log
to be
with the
positive.
first order.
So the negative sign makes the line decreasing.
K is always going to be positive, yes. K is always going to be positive.
And then the negative sign will make it decreasing.
Yes, yes, yes. The negative sign within the equation is what gives you that negative slope, yes. That's correct. Okay, so let's see, what does this mean? So here's something here. I have this here. I'm pointing these things out. And it says, use this to provided to determine the concentration of SO2Cl2 at 1,900 seconds. And just this one just tells you round to 3 sig figs. Don't worry about that in terms of determining the exact right sig fig. What would I do? I have the equation here, right? I plug in here, and then what? I solve for y. Am I done?
Yep. Oh,
No.
You just got the point.
What did I get? What does that tell me?
Gives you the natural log.
The natural log of the remember I went over this. Funny how I just said that about 5 minutes ago and how
Usually
quickly
why.
that goes right out when we try to solve a problem. This is the natural log of this. So I could get the natural log of this, but I'm asking you for the concentration, right?
okay.
Not the log of the concentration. Yeah, so I take the inverse of the natural log and then I get the concentration, absolutely. It seems more complicated than it is, so I like to point it out first and then you guys can take a look at the numbers. If I just go through the numbers and you'll say, oh, wow, that's an extra step. No, it's not. It's just, you got to think about what it is you're looking at. Okay. So I just plug in, there's a 1900. That gets me y. What is this here? Oh, so that gets me this here. This is this. This is also y is equal to this. So now I have to take the inverse of both sides of the natural log, which is that, and I end up with 5.78 times 10 to the minus 2. Is that okay? Not too bad? So you could look at the graph and you can solve for things, is the point. Okay. The major thing you can solve for right off just by looking at it is whether or not it's a first order or not. Okay. Try another one. When you look at a graph, just like when I said you look at a question, and I say you want to see what the reaction is first. When you look at a graph, what are the very first things you need to do if you're making it, or you need to look at if it's already made for you?
You have to look at the dependent.
You need to know the axes. Absolutely. Thank you, Taylor. You have to look at the axes. You have to know what it is you're looking at.
Yeah.
That should be the very first thing you do. What is it?
What are you comparing?
What are you looking at?
What am I defining?
And you have the time, and then you have the log of concentration. You have a straight line with a negative slope. Okay, I have a first order reaction, I know that. Is there anything different about either of these two things from the last one?
Is that
The log?
This is log to the base 10, not the natural log. I have to account for that.
Oh,
Okay? So there's one thing I have to account for, but what did I have to do first? I had to identify it. Right? I don't just say, oh, there's a graph and let's start doing whatever. What is the graph telling me?
right.
Just like when you make it in lab or anywhere else, you have to know what it is you're making, so that when somebody else looks at it, they must know what it is you're looking at, right? It's not just, oh, it's just the first order, it goes straight down backwards. Okay, there. So this one has to be adjusted for the natural log. So the adjustment now
It's gonna be 10 of
is that when I look here, I'm looking at the slope here. The slope is now equal to negative k divided by 2.303. This is the conversion to make the log to the base 10 the natural log. That's all you need to know. Nothing more than that. In terms of if you have on the y-axis log to the base 10 as opposed to the natural log, if this was just the natural log, ln, what would the slope be? Negative k. But because it's log to the base 10, I have to convert that to the natural log because of the equation. So there, you just divide by 2.303. That's it. Okay? But I want that to be clear. I also don't want it to be confusing. So I don't want to walk you through the derivation of it as though it's a big deal. It's just a conversion between the natural log and log to the base 10. That's it. So then, k, if I divide this, and what am I doing here? Or I multiply this, because it's divided, I multiply it here, I move the negative over, I get k equals negative 2.303 times m, which is the slope, which is given. This is the slope right here. So I end up with k equals 4.6 times 10 to the 4th per second. Is that what it asked me for? Yeah, that's the rate constant. Go ahead.
How did you get the units for second to the negative one?
So you're going to assume that when you have the time here, it's given in seconds.
Okay.
And let me double check this. This was taken from the same data, I think. Is that what? Here, times in seconds. So you see that up top here. But that would be from the data. Whatever data you have, it would tell you would have to have this data and then the graph, or on the graph it should state it. If it doesn't state it, on an exam you could ask, but I would just assume it's seconds.
Can you explain it one more time?
Example
Example 2.
2. This one?
Yeah.
Yeah.
What are you plugging in for x to get that 2 number? That
I'm putting that
2.303.
2.303, that's what I'm
Isn't it 0?
Guys, it should go.
Log to the base 10
Yeah.
Right. It's 10 to the 4th.
versus log, the natural log. The 2.303 is just the conversion to get you from log to the base 10 to the natural log. So when, so when you have this log here, then this, you have to account for it by dividing by 2.303. That's it. You just now converted the natural log, or the log to the base 10, into the natural log. That's all you did. These two things, you guys know this, right? Is ln equal to log to the base 10? Those are not equal,
No.
right? This is just the conversion so that I go from this log here to that one. That's it.
Okay.
It doesn't change. If this said natural log, you don't use this. If this says log, L-O-G, use that. That's it.
We use 0.002 divided by 2.303.
Say that again.
Right. Well, no. You gotta first get y, and then you can use the conversion.
Oh, you have to find slope, then you divide it.
What is this question asking for?
The rate.
It's asking for K.
Yeah.
And you know
I don't have to do anything with X or Y here.
Because you know it.
Okay.
Because in this, the slope is
You
given.
have the
The
slope.
slope M is equal to negative K if it's a first order reaction.
Gotcha.
So then you just cross multiply.
I don't do anything. All I do is plug in for M to solve for K.
So he was
M's
right.
given.
Yeah.
Negative 0.0002. If I plug this in directly here,
Mhm.
then I just multiply this to get rid of that, and I divide by the negative, I get a positive, and that's what my K is.
Right. So 0.00.
This 2.303 is only the adjustment because this is log to the base 10, and I want to go to the natural log because the equation's set up with the natural log, if you remember, right? Let me do this. Maybe I should take you back to make sure that that's.
It was on there.
See, this here is based on natural log. So if I'm now looking at the log to the base 10 here, I have to have that, I have to do it through each step, right? I can't just do it to one part of the equation.
Yeah.
So in order to convert it to each step, that means this is the natural log, or this is now the log to the base 10, log to the base 10. This also is affected by that, right? And it's affected by a 2.303 conversion. That's it. That's all that is. Does that help a little bit?
Yeah.
If I gave you this with the log to the base 10 and log to the base 10, then I'm not doing anything from that chart. But if it was natural log, then I would have multiplied by 2.303 in order to get it back to the log to the base 10. But because it's based on this log here, the natural log, then if I give you it in log to the base 10, then this needs to be converted by dividing by 2.303. And now I'm dealing with the natural log all the way across this equation. It's the same number every time. It's just a conversion. That won't change, right?
Okay.
It's always 2.303 in the context of the slope if you have log to the base 10 and not the natural log. But if you have the natural log, then you don't make that conversion. It is what it is.
Got
Does
it.
that help?
Yeah.
Where am I at now? This one? This one? One of these, right? Okay, so I did this, and then, okay, so that's all that is. I should say, just to make sure this is clear, the slope here is negative, right?
Yes.
So I put that negative in here, which is how the negative times a negative becomes a positive, because K has to be positive.
Yes.
Okay, yeah, I want to make sure that's clear too, because they kind of skip that step. That would be the only, and then here it tells you, it specifies round to 2 sig figs, so you're not really dealing with sig figs there. Okay, is that okay now? That's a pretty easy problem, right?
Yeah.
Once again, don't get tricked by the log and the log to the base 10 of the natural log. That's the only thing that this is really supposed to be pointing out. If this was just natural log, what would the M equal? Negative K.
Yeah.
That's just negative K. So then negative times negative is positive, right? And that's just this. That's K.
Yeah.
2.303 is just the conversion between natural log and log to the base 10. Okay. So, what do I have? Okay. Now we're going to transition this. What kind of reaction was this? First order. Now we're going to transition to second order. Okay.
Same thing applied.
It's going to be slightly different, but we're going to do the same kind of thing. We're going to do exactly what we did with the first order, but now, of course, the equation is going to be a little bit different for everything because you're starting with a different integrated rate law for that, right? So if I look at you're also starting with the different rate law, right? Which then is what translates into the integrated rate law through some calculus magically that I'm not showing you. All right. So I have here, this would be the rate law for a second order, right? And once again, I'm working with something very simple here, right? What is the key that I'm showing you in these? What's the very first thing you should always be thinking about in these? What's the reaction? So how many reactants do I have? That makes these equations make sense, right? Dealing with one reactant. What if I had multiple reactants and things like that? That gets a little more complicated, right? So we're looking at these, this is just one reactant. That's why I don't have multiple things. That one reactant, and I'm looking at the order of that reaction based on that one reactant. So this is another decomposition, but now it's second order, not first order, okay? Which is, here, so I make the first order based on this, and now I'm making the second order based on that. Okay. Differential rate law, which is the integrated rate law, using calculus. I manipulate all this, and I end up with this. This is the integrated rate law. So what do you need to know? You need to know this one if you're using the integrated rate law. What's different about this and this? And by the way, if I wanted to replace this, what would I replace this with? The rate. That's the rate. That's the very first thing we learned in this chapter.
Right, the rate of
Right? For this,
reaction.
this is the rate, which would also correlate to whatever the products are as positive, right? This is the rate, set up in the rate law as a second order. I now convert this into the integrated rate law, so this one allows me to correlate the rate to the concentration. This one allows me to correlate the rate to the concentration and the time. This is just the second order one, not the first order. Okay? So this is my second order integrated rate law. Is that different than the first order integrated rate law?
Yeah.
Yeah, absolutely. Why? Because I'm starting with something different here in the rate law, right? I'm starting with that. Not the difference between this and the other one would be that 2, right? That's the second order versus the first order. Nothing fancy here. This is, I'm building up based on what you know. I'm just making sure you remember what you know to see the new thing, right? That's all, okay. So let's take a look now. For this reaction here, I have a K, I have the initial concentration. I want to know what the final concentration is. I'm going to tell you that this is a second order reaction. Okay, a lot of times as we go further, you're going to have to figure that out through some means, which we'll discuss. But for now, at this stage, I'm going to tell you this is a second order reaction. What would I do to solve for this? This is what I'm looking for. What would I use?
The formula we just saw, so it's.
The integrated rate law. Why would I use the integrated rate law for a second order reaction and not just the rate law?
Because the other initial formula.
Would the rate law allow me to figure out what a concentration is at some time point? No. Would the integrated rate law tell me that? Yes, because it's related to the time. So then if I'm using the second order reaction here,
You got K.
what am I solving for?
H.
This one, right?
Time.
So do I have this? Was that given?
Yep.
Was this given?
Yep.
Was this given?
Yes.
Yes. Where was this one given?
On the little subjects. It's from 0 to that was
That.
6:45.
That's your time.
I'm assuming it's.
Seconds. And without it saying it,
Oh,
seeing
yeah.
this here, now it must be. Unless I tell you something different, but 6:45 would be a lot of anything if it wasn't second, right? At least for a reaction. Okay, so I have this here, I plug in these, there's my K, here's my second, came off of this, and what did I do? I put this here, here's my initial concentration, I can now solve for this. Remember, this is 1 over though, that's another mistake people make.
Yeah.
They go ahead and they solve for this, and then they say, but I'm asking for this. So then you have to move this up and take 1 divided by whatever that is at the end. Okay, and then I take this, I move it this side, I take 1 divided by that, and I should get 0.0012 molar. And that's at 645 seconds of this second order reaction. If I start at 0.0030 molar, I end up with 0.0012 molar. That's what that tells me. It tells me the concentration that I have left in this reaction based on the rate and the time associated with that rate and the initial concentration.
The initial time was given?
Yeah.
It's funny, that's okay though. See, sometimes people think differently, so it's a drip, drip, drip is information. So where did you figure out where the time frame that you were looking at here was?
Right.
Went from 0, the original,
Okay.
to 645 seconds. And see, those are things that when you're doing them on your own, you have to recognize it's not as easy. Because remember, I walked you through that. So those of you that got it, I said, where is the second thing?
Right.
Right? And that's, when you're on your own and you're thinking on your own, this is where the disconnect between being in here with me describing it and leading you and you being at home without that. This is where you start to find the nuances of, oh wait, what does this mean? Where did I get that? Oh, did he say this? Maybe you make the connection. Maybe it takes you 5 or 10 minutes. This is where you put good notes down, right? Because they're not stated in it. But then when you can do that on your own at home, when you get in here for an exam, you're okay.
Absolutely.
Yeah, exactly. That's exactly right.
So are you taking 1 over 8.3 times 10?
Yes, I'm taking 1 divided by this, because this will move up, and that gives me this.
You could also put it to the negative 1 power, and that'll make something.
I put what to?
The 8.3 times 10 to the 2. If you put it to the negative 1 power, it's a little bit.
If you bring it down, it's already down as positive.
Let's just say, let's just look at it. Make sure that we're not, make sure we're not confused. 1 over this thing equals, let's just say 9 m to the minus 1, right? Okay. Multiply both sides by this. Multiply by a, cancels. Multiply by a. And then you're dividing this, right? 9 m to the minus 1, so that cancels. You're dividing 9 m to the minus 1. Now m to the minus 1 underneath goes up, right? And now it's 1/9 m equals this. Becomes positive. Is that what you said?
It's also the same thing if you took the 9m to the negative 1 and put that entire thing to the negative 1 power, it'll flip the entire thing over.
Yep. Is that okay? Just make sure that's okay. Okay. So now let's take a look. In the first order, we learned the integrated rate law, and then we did an example or two or whatever we did. And what did we do after that? Half-life. We did half-lives, right? So if you remember, what does half-life mean? I just make this 1/2 a to the 0, the initial, right? Okay. This. And I just take this and I plug this in here, right? And if I do that, I get this. Same thing we did before. What does half-life mean? I want, for some reason, and even when I was an undergrad, I think I got confused a couple times with this. What does it mean?
To reduce by half?
Time for the concentration to cut in half. Why do I ask that? Because a lot of times it's tricky. When you think half-life and you hear that term and you see t to the 1/2, you're saying, oh, when the time cuts in half. No. The amount of time it takes for the concentration to cut in half. Okay, that's the distinction I'm making, because sometimes that's tricky. Okay. So then what do I do here? If I move this over, I get 1 over 0.5 over this, minus this gives me what? Yeah, but if I take this and I subtract this from this side, that becomes 0 here. And I subtract it from here, what am I left with over here?
Oh.
This 1 over the initial concentration, right?
Right.
1 divided by 0.5 is what? 2.
2, yes.
And I'm subtracting 1, I'm left with 1, right?
Yeah.
Okay, let's just make sure that we're seeing this, right? So that's where I get this kind of thing, and I end up with this.
Yes.
Because now I just moved the k down. So what I did was I did this here, and I get this. I just want to make sure that doing this is clear. 1 divided by 0.5 is 2, 2 minus 1 is 1. Okay, okay, right. I know that will come up, that's why I wanted to make sure that I thought it was clear, just in case though. Now I have this equals this, and I want to find the t half-life, so I just move the k down, and now there's my half-life equation for a second order reaction. Okay, no big deal.
Mm-hmm.
You don't have to know how to, you don't have to memorize the derivation, you just have to know the equations. I try to give you as much that's reasonable to explain how I got from one thing to another. But it's not, I'm not gonna ask you, how do you derive this? Right? How's this different than the first order half reaction from an integrated rate law?
The KT plus.
It's what?
It's not in a straight line, it's gonna curve. It's gonna change.
Okay, we haven't got to the graphing of this yet, so let's not worry about the graph. Let's just think about the half-life.
No, it's not
What's
the
the
right time.
concentration?
What was the half-life of a first order? Maybe we should write that, right? Well, what was T1/2 of a first order equation?
Oh, okay, yeah.
0.693
Over time.
over K. Was negative or positive? Okay.
Yeah.
How's it different than this one?
This one.
This one depends on the initial concentration. It's dependent now. The initial concentration matters. Did it matter here? No.
Is it inverse of the rate?
What's that?
Is the rate equal k times the concentration? So this is the inverse of the rate.
This one?
Inverse of the rate. I'm not sure about what you mean by that, inverse of the rate.
Oh, wait.
The rate
No,
itself
This is 1 over x.
is what? Let's try to see what you're getting at.
It'll be 1 over.
I'm not sure why this matters, actually, but if you're interested in, let's see what you're getting at. So you have the rate for a second order is going to equal k this, right?
Yeah. Okay. Never mind. I got it.
Okay, that's cool. So here, we're looking at the half-life. What are we, once again, what does that mean we're actually looking for, which might help as well to why
Concentration.
we're looking at where the initial concentration is now half. At what time it takes to get that. And that now matters on the initial concentration. It doesn't matter for a first order, but it does matter for a second order. It also, I should just say, since I probably won't talk about it too much, it matters for a zero order as well. The initial concentration matters for both.
Can you kind of explain why? Like, I'm trying to think about intuitively, like, why that would affect it.
We'll see. We'll take a look. We did look at the half-life of the first order, and we saw a graph of that, right?
Right, the graph, right, that was important.
What did that graph show? Sort of a
Straight, right, straight.
And we saw at every 100 seconds that was on that one? Is that what it was,
Yeah.
10 seconds or 100 seconds or something? That at every 100 seconds, whatever the concentration, the initial concentration was, you had exactly half, right? That means that in this case, that won't be the case,
True.
It's not.
right?
Yeah, every 100.
Is that what that was, every 100?
Mhm.
Right. So think about it that way, and then when we get to it here,
Suppose you
then make
rest
the
in the
correlation to how it's different, because it's the
concentration
difference between a
times
first order and a second order.
Right.
And we just did the derivation, so we could see mathematically that's definitely correct, right? There's no doubt about mathematically. What was maybe we should quickly look at, what was the rate law for this one, for the first order? The integrated rate law.
It was A time over A0.
What is this one?
That's a final, so
AT
AT,
over
Over
AT over AW,
AO
AO.
for
AO.
equals
Equals?
negative KT.
negative KT. Okay. And when we made this half, all I did there was this, right? Right?
Yep.
Those cancel, right? Log 1/2, or let's just say 0.5 to make it easy. is equal to, right? Which is then equal to KT, right? Then I divide by K, and that's what I got. These things cancel. They weren't relevant to the half-life. That's how we got that equation, right? Didn't we derive that?
Right, yeah.
Did I leave some of that off? I don't remember now. I might have thought it was easy enough to be okay if I left it off. And now we just did the derivation here, and mathematically we can clearly see that the half-life does depend on the initial concentration in the second order, and the half-life does not depend on any concentration for first order. Starting with the integrated rate law, and then making the adjustment at half that concentration, which is why we went, that's why this piece here matters. I'm putting this in where the T was before, right? Whatever that time was. But now I'm saying it is at that time, T1/2, which allows me to do half of the concentration. So mathematically, you could see that. We talked a little bit about intellectually what this looks like. So now we'll get into this one as we take a look at it. So half-life does depend on the initial concentration, and the half-life increases as the reaction progresses, where before it didn't matter. It was going to be the same. Okay. So I'm given a K here. How long does it take the concentration to decrease half? Okay. Now, what I want to point out here is we are talking about a second order, so that's given here, and it does say second order here in the lecture series. Remember, these questions are going to be juxtaposed on an exam. Keep that in mind. It's not going to be in this nice sequential order. That makes it harder all on its own. Okay. Now, the second thing is, if I look here, my instinct on an exam, hearing other people scramble around with their pens and whatever next to me, I might get nervous, and the first thing I might want to do is, okay, I want to put this into the integrated rate law because I have two concentrations. Take a step back and recognize that the two concentrations, one is half of the other, which means that you're just dealing with the half-life, which is going to be easier than using the integrated rate law equation. Would it still work the same? Of course. But it's a lot harder to work with. So what I'm saying is recognize that this is half of this, so I could use the half-life. If this was not half of this, then I'd have to use the full integrated rate law. Okay? Just one way to evaluate really quickly what's easier, what you should use. So it says, how long does it take? So I'm looking at the time here. So like I said, I could put this into the full integrated rate law, but why? Right, let's just use that one we had here, right, wherever it was, the other one.
We didn't write it down.
T1/2 equals, what was up top? 1
divided by K.
divided by K times the initial concentration. Simple, I have the initial concentration. So, there we go, just like that. Could I use the whole thing? Yes. Are you taking a big risk of making mistakes? Yes. Okay, so then I just plug in, chug, and I get 430 seconds. It's okay. This is just plugging in the calculator, so I'm not going to spend too much time on it. That's when I say plug and chug, literally you're just using your calculator. And I know you guys at this level are much better than that, so I'm not going to worry about it. Unless it's a tricky kind of calculation, then I might say double check you can do it because you don't want to make a mistake on the example. Okay, so what would you expect now, knowing this? What would you expect now? So remember, if you look at the chart for a first order, and this goes to Dieter's question, if I go from a first order and I plug in whatever initial concentration, am I plugging in a concentration here? No. My rate constant throughout the reaction, is that the same? Yes. So it's always going to be the same half-life, no matter what I'm starting with.
Yeah.
That's what that means, right? In this one, the concentration matters. It will tell me a different amount of time it takes to get to the half-life based on that initial. Right? Is this helping a little bit, Dieter, what you were asking about, how it's different? Yeah. Okay, so why? Now with that why, going back to your question, why does it matter?
Because
think about the big picture first.
It'll tell you the time.
But think about the big picture, what's happening? You're decreasing the concentration of the reactant. We talked about this early. Not today, but we talked about this before. When you do that, in general, what is your instinct to what will happen? I end up with less reactant. Is that going to speed up or slow down the reaction? Yes, it's going to slow down. Hence, it matters. So this should go up or down? Go up. Does that help with you guys? Okay. Because it's now going to take more time to cut in half, right? Because the reaction's moving slower, because you have less reactant to react. That's the nature of a second order reaction.
Right.
And a big difference between the first order, where it doesn't matter how much I have.
Sorry,
Which also means what? We talked about what the difference is at that point, what that meant. A first order. Doesn't matter about what the actual amount is. Why? I have excess of it, maybe. I have so much of it, it doesn't matter. It doesn't matter how many half-lives I have. It's a first order. I have so much of it, it makes no difference. What else? Maybe there's a bottleneck somewhere. And in this particular one is not one of the things that's causing that bottleneck. So you always have plenty of it to get through. Remember, are these reactions always linear in these basic formats, or are they multi-step? Multi-step. So in one of the steps, there's a bottleneck. And the thing that this part of that step is occurring is not causing that bottleneck. So it doesn't matter how much I have here, because there's always plenty of it to get to this point. Something else is causing that problem. Okay, so there are a couple different reasons why you have a first or second order, and what it means in the context of a reaction, based on how extensive that reaction is, how many, what the mechanism is, how many different substeps there are. We'll look at transition states of things that are more simple and stuff like that coming up. Does that make sense? Mm-hmm. So that's why these things matter and why they're different. Okay. Oh, another part of this question. How long does it take the concentration to half again? You would expect it to what? Probably double, and this is now going to be 15, 0.15 or whatever it was, right? 0.015. 0.015. Okay. Very good. So then you plug that in and you get the half-life of that, and as you see, it goes up because the reaction rate went down by about half.
What did you just leave it a multiply by 2 from the first time?
Multiply the first one by 2. So I would warn against that, because there are circumstances where it may not translate exactly as half and double and all that kind of thing. And this is a second order, so we have touched on a first order and a second order, but we haven't talked about, remember there were a couple other types of orders? There was a negative order, there was a half order, there was a zero order, and those things can become confusing. I would just use, this is a pretty simple equation, and if you knew the first one, you might anticipate the second one, but I would still plug it in and verify that.
What if it's an increase from 0.0015 to 0.0000?
So you want to increase,
So opposite.
you want to increase the reactant?
So is it able to switch it? So from
So keep this in mind. I kind of like how you're thinking, because it's being creative, but the problem with it is you're looking at how the disappearance of something is, right? So it's not you're not speeding up the reaction the moment you add it. You could then say, at this moment, how much of it disappears. Does that make sense?
yeah.
But I like the creativity of that. And if you were looking at a product, then you would be looking at the inverse is what you're trying to get at, but not necessarily by adding more, just by the reaction moving forward more. But in this case, you're looking at the decrease of something. So by adding more, then that's just your new initial point, right? Okay. Now let's get into the graphing. So I'm taking this here. This is the same as the integrated rate law for the second order. And I'm going to correlate this to y equals mx plus b again. Okay? There's my y, there's my m, my x, and my b. So what's different here?
It's
Positive. So then slope is going to be now positive. It's going to be a straight line. It's going to be a straight line with t as my x again. But now it's 1 over the concentration of the reactant, right? As opposed to the natural log of the concentration of the reactant. two different things. No, that's not inverse. Those are completely different. Keep that. Yeah, so don't get confused by that. Okay? So I'm graphing this relative to this now. Okay. So let's take a look. Okay, now, if I'm looking, so I might say, what is the reaction rate of this particular thing? What is the order of the reaction rate? And you have a graph, or you don't have a graph. Let's say you have data and you have to graph it. The first thing you're going to do is you're going to graph it with what? Log, natural log, concentration of the reactant per time. And what are you going to look for?
Slope.
You're going to look for a straight line
Yeah.
that has a negative slope.
Yes.
If you get that, do you know what the reaction order is?
Yes, one.
1. What if you don't get it?
Then it's gonna
Then it's not 1. You got something. Yeah, absolutely. 100%. You don't know. What can you now try to do? Well, I could now take 1 over that concentration per time
Yeah.
and regraph it.
Yeah.
If I get a straight line positive, it's a second order,
Yep.
right?
Uh-huh.
If I don't get it, then what? It's not a first or a second order. I don't know again,
right.
because those are the two that you know. I'm not going to introduce. I guess I will show you probably a zero order, but usually focus on first and second because that's usually what the rate is. Remember, a zero order is just usually 1, but it does have its own rate law and everything else that I'll talk about. So that's what this series is saying. Collect time versus concentration data, assume it's a first order, plot the log, this should be natural log, of the concentration of the reactant versus time. If it's a linear graph, you have a first order. If it's not, then plot 1 over the concentration of the same data. And then if that is a linear, then it's a second order. This implies that that's all you can possibly have, but of course, as you know, that's not true, but maybe for this class it is. In other words, it makes it a little easier to have these parameters.
So for number 3, it has to be, because it's first order, it has to be decreasing, but then for number 5, it's second order, so it has to be increasing.
Yes, that is true, but that's not really the first thing I'd evaluate. First thing I'd evaluate is this a straight line or not? Right? It will be negative just by the log. But it could be negative as like this. That's why I wouldn't necessarily think of it just as if it's a negative slope. I would really be looking at, is it a straight line or not? Let's take a look. Well, I'm sure we're going to try it. Okay, so here's experimental data. So here's time, here's concentration, presumably of a reactant. And I want to know if it's a first or second order, and I want to determine the rate constant for this reaction. Okay. So what can I start with here? What's the first thing we always kind of try to evaluate as much as we can? What's happening, the reaction type of thing. So I can say I have what, NO, was that NO2? It's going to something. Okay, maybe that's as much, maybe it's going to N2 plus O2 if it's breaking down. So then what do I want to do here? Got to go 2 and 2, and then probably this is what's happening. Okay? Now, I want to know the rate of this. Rate equals what? Okay. Concentration of NO2 and X. I don't know. So what is this asking me to find? It's asking me to solve this and this, right? All of those integrated rate laws that are so neat that we just did, can I use one for this up to this point in my knowledge? No, why not?
You don't know that.
I don't know the order. I don't know X. Thank you. This is all I know up to this point. It's asking me to find this and this. Maybe once I find this, it will make this easier because then I could just put it into an integrated rate law since I don't know the actual rate. But for now, this just allows me to see what is it asking me for and why I can or cannot use something based on all the things that I know. I can't just jump in and call this 2 or 1. I don't know that. But I have data. From the data, I could make graphs. From the graphs, I could determine this. From that, I could put in the integrated rate law based on what the data tell me in terms of the order. And from then, I could find the rate constant, which is what it's asking me for. So that's my plan. When I look at this, that's what I see. And I say, well, this is what I know. That's what I want to find. That's how I could find it. What happens on an exam, if you're not as comfortable with this, is you start trying to force fit an integrated rate law. You don't know that yet. You don't know what the order is in order to use an integrated rate law. But you do know how to figure that out if you graph the data. Okay. So, first thing is I'll plot log. That really should say natural log. I think I'll usually give you natural log, but just in case LOG, I think that's probably off an old textbook. I think the newer textbooks use LN. If the plot is linear, the reaction is first order. Okay. If it's not linear, then I'll plot it this way. And if this plot is linear, then the reaction is second order. So this is how I'm determining my x. Go ahead.
Is it supposed to be natural?
It could be either, because you can make the conversion by 2.303. But I prefer natural log, which is why I said that. And I think your textbook usually uses natural log. So let's do the first plot here. So here, we're going to do the log there. So here's my time. Here's the concentration. From this, I get this data. Also from this, I get this data. So I have the data to plot to see if it's a first order, and the data to plot to see if it's a second order. Right? If I just had this here, I take this and I can figure these out. I have to know what I'm trying to figure out, of course, but that's pretty easy, right? I just take, in this case, I would have used natural log, but in this case I use the log of this, gives you that, the log of this, and then I just put 1 over this, I get that, 1 over this, etc. Right, so I take the first 2 columns of data, and from the second column I get the third and the fourth columns. This allows me to plot versus this for first order. This allows me to plot versus this for second order.
Nice.
If whichever one, you follow what I'm, yeah. Okay. So I plot the first one, the log of A, concentration versus T is still, you have the still negative slope, whatever, and is it a straight line? No, not a straight line. What does that mean?
It's not a first order.
It's not a first order. So I know that this is not 1. Okay, now I plot those 2. And, oh, look at that, it's a straight line. That means what?
Second order.
Second order. What does that mean? I could now fill in my x here. I just solve for x using the data. Second order. That's great, right? Because that also means what? 1 over the concentration of what?
NO2.
NO2. And that equals?
Okay.
Okay. What else?
T
P
plus
plus
1
1
over
over
Concentration initial.
NO2.
NO2 initial.
Which one's initial?
That one.
Okay. So from that, can I potentially solve something?
Yeah.
Do I know different points of these? Can I figure out the time that it took for the different points?
Yeah.
And then can I solve for K? The rate constant? Go ahead, David.
How do you know that it's a second order? I thought if it's linear, then it would be first order.
Because it's going up instead of down.
Come on, Data, look,
Oh,
look,
that's
look.
right, that's right.
Because I first tried this versus this. This is with the log concentration, and it wasn't a straight line. So it's not a first order. So then I re-looked at the data and I tried this and this. So remember, this is for what? Integrated rate law for a first order. This is
Integrated for second
for a
order.
second order. So now when I do that one, I do get a straight line. So this axis here is what? 1 over concentration. 1 over the concentration time by time. Straight line is what? Second order. Absolutely. Okay, so now, okay, or I could just get the slope. So I could have done this, right? Or I can get the slope from what? The actual graph. So if I take the data here, I'm looking here, I want to just take 2 points, right? Here to here, and I get my slope. My guess is they'll go, a lot of times it's easier to use 0, right? So you get 379 minus 100, and 360 minus 0 is just 360. So sometimes, but you could do it in between, doesn't matter. And let's see what they do. 379 minus 100 over 360, and that gives you the slope. Whoops. And now what? The slope, is that what you asked?
Yeah.
Okay, then you're good. Is that okay? Okay, here's a mop-up slide of the whole thing. Zero order, first order, second order. I like this slide because it kind of, if I'm you guys at home studying, I would take this slide and just use this so I have everything already there, right? It's a summary with everything. So here's the rate of each one, zero, first, and second order. Then I have the units of K, what they usually are, of each one. You see how they're different? That should make sense because you have one squared, you have one just by itself, and then you have one that's gone because it becomes one, right? So that's why this is molar per second, this is just per second, this is per molar second, right? And you could just do that by putting them in here, right? So if this is s to the minus 1, and then whatever you have here is m2, so then the m2 is canceling out with some things from the k. Remember, the k is different depending on what the order is,
Right.
in terms of its units. That's what we talked about very early on. Maybe it wasn't as obvious back then as it should be now. Anyways, units are here. Here's the integrated rate law for each. So this is something you know. This is the difference, but these two things hold up for the integrated rate law for first order. Here's the second order we just talked about. And then there's the zero order, which we didn't talk about, and that takes some other fancy calculus in order to get that. So it's here, if you ever needed to use it. You could see here that the straight line negative slope for a zero order, this is one you hadn't seen before. This is just simply the concentration versus time. Once again, I want to point out, make sure you understand what the axes are, what each one is, because that's the key to understanding it. This is the concentration versus time, this is the natural log of the concentration over time, and this is 1 over the concentration per time, and that's what gives you a straight line accordingly to determine what order you have, if you have just data and you don't know anymore. And then here are your half-life expressions, and here you could see this equals this, which also equals that, which is the same thing, just separating those. And you can see this is dependent on concentration for a zero order. Here, a first order is not dependent on concentration, and here the second order is dependent on concentration for the half-lives. So that's the 1 and the 2 that we did, and you have zero order as well. Of course, we did more than that, right? We looked at a half order and we looked at a negative, but those are not going, you're not going to deal with graphs associated with those, at least in this context. Okay, so I like that one. So let's do some examples, hopefully get through this section here. Here's some data for, so how is this reaction different? Let's start with that. Just off the look at it. Two reactants, right? This is now a little bit different than what we've looked at because this has 2 reactants. And I have data, and I have data for each one. So with the 2 reactants, what does that give? What can I use that I've learned up to now in how to solve for orders? Compare them. Look where one doubles the rate, and what happens to the other, right? So here, going from here to here doubles, going from here to here is the same, so I could say when this doubles, what happens to this? Doubles.
Yes.
First order. Yes. Right. See, that one's easier. Little different than what we looked at, but very similar to what we looked at earlier, not since the integrated rate law. So we did that, okay, what did we get? Doubles, good, first order of that. What about the CL2? This one stays constant, it doubles here, what happens there?
First,
The second and third.
0.029, so the second and third, 0.029 and 0.041, is that doubling?
yeah.
No.
Oh, wait.
Oh,
What is it?
oh, it's slowing down.
By a third.
Oh, it's speeding up.
Which is 1.4 about times, right? So 0.029 times 1.4 would give me 0.041,
Oh, okay, so second order.
right? And that would be the
Second order.
square root. Remember the square root?
Oh,
Okay, so I heard second, so if this quadrupled, what would that mean?
Oh, right.
second
No,
order.
no, no. Yes. It's not quick.
If it didn't change, it would mean zero order. If it went up by 1.4,
Right.
that's the square root, then it was a half order. Half order, right? Remember that little chart that I took you back to multiple times?
Right.
So that's a half order. Right? So if I look there, as Cl2 doubles, increases by 1.41, which is the square root, which means that it's a half order for the Cl2. So based on that, what did this question ask us for, James?
The rate law.
The rate law. So now can we put in the rate law for this?
Yeah.
Yeah.
Yeah. Right, so the rate law is going to be the rate is equal to K times the concentration of CH3Cl to the first power
Where's the 1.41?
and Cl2 to the half power. What's that?
Where's the 1.41 from?
We need to find 1.04.
If I say 0.029 times 1.4, what do I get? 0.041. It went up by 1.4,
Right.
as opposed to doubling. If I say 0.014, right, times 2, that gives me 0.029
So
approximately,
we
or
divide,
2/8.
we divide the second one by the first one
Mhm.
to see if it changed, right?
When I double the concentration, what happens to the rate? That's what I'm asking. I doubled the concentration of one. What did the rate do? In this case, the rate doubled. In this case, the rate went up by 1.4, which is the square root of 2. Anybody else? Oh,
Can it be like an approximation, like if you multiply it by 2, you get 0.028? So.
yeah, it's close enough.
Okay.
Sig figs, rounding, all kinds of different things could create that slight difference. Anybody else? It's okay? Okay. Okay. So let's write the rate law, and there we go. Is that all it asked for in this question?
K.
Okay, so now can we solve for K?
And you go concentration.
I could take any one of those, right? 1, 2, 3, or 4. I could put in the concentration, say here, 0.2, 0.2, and then take 1/2 of it in this case, and then take 0.115 here, and I solve for K. I could use any one of the 4.
Right.
Doesn't matter which one I use. Probably use the first one just by convention. There you go. 1.3, negative 1/2 molar, and negative 1 second. And that's my K. This is very similar to what we did earlier, except for now we have a little bit more knowledge, and now you just have to know when to apply that knowledge depending on what the question's asking. I want to get through a little bit more. How are we doing? Still see some people writing.
Oh, that finished at 20. 12:20.
I think it's 25.
25.
Yeah. I wish it was like 35 or 40 or 50 so I
Or
can get more
one.
through more.
Yeah.
But I don't want to go too fast.
This class is only like an hour and something. 11, 12, 2. Yeah. An hour and
Okay,
20
graph
minutes.
below. Prepared for this reaction. So the first thing I do is I look at this graph, and what am I going to look at?
The 1.4.
What are the axes? I'm not changing my answer. I'm going to tell you the same thing every time. What are the axes? Time versus 1 over, linear. Before I've even done anything, what do I already know? It's a second order reaction. And it even gives me all this stuff here with the slope and everything. Wow, this is great. Now, AB, so that means this is really, should be AB in here, right? And it says determine the order of the reaction. We just did that. It's second order, right? What about the value of the rate constant? Can we do that? It's just the slope. Is the slope given?
No, not subtract.
It's given. Wow, that's a pretty good. All the problems are going to be like that on the exam. And the second part is predict the concentration of AB at 25 seconds. Well, once again, that's pretty easy, right? I just plug in 25 for X. And I solve for Y, and then I take 1 over that in order to get the actual concentration. Remember, this isn't concentration, this is 1 over that concentration. No big deal, this should be a really easy problem. Determine the rate of the reaction. Okay, now I have to figure out if I have the concentration at starting at what, 0.10 molar? So if I have this concentration, then can I solve for the rate? Using what? The rate law. 4A, second order reaction. Because it's already given here that this is the only reaction. Does that just be the rate equals K times the concentration of AB squared? Yes, power of 2. Once again, no problem, right? Okay, let's take a look.
Or the other way.
Graph 1 over A. In this case, it's actually 1 over AB concentration, straight line, it's second order. Okay, we just solved that pretty quickly. Then for K, it's already given since K is M. Whoops. Right? 0.0225, 0.0225. If I wasn't sure of the units, what would I do? Go back to that chart, the summary chart, and see. No big deal. Why I have to memorize everything like that, right? Okay, so far so good, right? That's why I said, wow, this is a pretty simple problem for you guys. Rate law, what's the rate law? Oh, okay, so first they want to find the concentration. So we're just going to plug in the 25 into this equation that's already given here, right? 25 seconds is the time part. You're going to get Y. Y is equal to 1 over AB, so therefore I solve for the concentration of AB. That comes up, this goes down, 1 divided by that gives me 0.617 molar. I put that into my rate law for a second order. I know K, I know the concentration, I square it, and I get my rate. Oops, make sure everybody got that, it's okay? Is this in the notes? Do they?
There's no details.
Okay. I'm in the text, so go ahead and let people write that down.
Yeah.
This should all be fairly easy for you because we've done it multiple times. Hmm? Yes, this is just AB. It should be AB. Not a typo, they just used a different graph. So it's locked in, you can't change it.
Can you tell me how you did the calculation for AB one more time, like where it's the Y equals?
You do 1
This is-
divided by the number that you have.
This is what?
Right.
1 over concentration. Remember the integrated rate law for a second order?
Yeah.
Remember how it lined up? Y equals mx plus b? Y. This was your Y. 1 over the concentration.
Okay.
Right? Over time, that was your x. Your slope was k. That's your b or your y intercept, which is b. So then when I'm solving, when I put this here, the time is x. I put the time into x, I'm solving for y. I'm solving for whatever's on the y-axis.
Oh, okay. Gotcha.
Right? When I solve for that, so that's the 0.0225. There's the 25 seconds, I'm plugging in for x, that's the time, plus the 1.059, which is given. I solve for y.
Right.
Y equals this.
Correct.
Now I have to solve for the concentration within y. Because the concentration isn't y. That would be for a 0 order, right? So that's why I always say, what's the first thing I say when you look at the graph? What are your axes? What are you looking at? That's the whole point of that statement. Does that make sense? So now I'm solving for y. Y is equal to 1 over the concentration of AB. So now I have to solve for AB. So I move this up, I move this down, 1 over this. That's my concentration of AB.
Oh, okay, so it's 1 over the 1.622.
Yes,
Okay.
this is the
Okay.
division sign like that, yeah. This is 1 over the concentration of AB, so I move the AB up, I move that down.
That's okay.
Now, what is the rate? It's equal to K times the concentration of that squared, right?
Mm-hmm.
K, we know it. If we don't remember from the all the writing from before. We just look back on this chart, right? AB we just solved for, but we're going to square it since we know it's the second order based on the straight line.
Based on this information, can we find out the concentration of 1?
Give me 1 second. Here's your rate. Now, what was the question?
Oh yeah, based on this information that we got thus far,
What
can we
information?
find this information, like the concentration of AB? Can we find the concentration of just one of the reactants? Or not enough information here?
This is the reactant. It's only
Right.
one
We
reactant.
have one,
But can you find the concentration of just A?
like breaking.
Of a
it
product,
apart.
you mean?
Of, oh, this is the product. Yeah, of one of the
That is-
products, correct.
So if you know the concentration of AB in moles per liter,
Right. Then you do the conversion.
what would you need in order to
conversion.
solve for the concentration of a product?
Balance equation?
You need the balanced chemical equation. What else do you need? What kind of stoichiometry is Hurley asking here? Solution
Oh, the limiting
stoichiometry,
reaction?
which means that if I knew the volume,
Right.
I could then figure out the mole, and I use the molar ratio for a balanced chemical equation to determine the moles of the products.
Right.
And if I knew the volume I had it in, like a titration curve, then I could then figure out the molarity of that as well.
Gotcha.
It's okay?
Yes. Back to square one.
Back to Chem 101.
Yeah.
Is that okay? Everybody see that?
Yeah.
Okay, now, before I let you go, really quickly, I just want to put this in your head because you're going to have the weekend, and then when we come back on Tuesday, this is what we're going to talk about, so I want you to think about this first. Rate of the reaction obviously depends on the temperature. The temperature is integrated into K, and I've groomed you from day one on that, so that this should be very simple. What I want to point out is we're going to get into this equation here, and K is equal to this. I'm breaking up, I'm unpacking K now. Remember I told you I'd do that?
Yeah.
What I want to just point out is this A is going to represent a couple things that we'll discuss later, but I call this the frequency factor. And this series here is called the exponential factor. Within this, you have the temperature, the gas law, and the activation energy, things we already discussed. And within this, you're going to look at number of things that time something interacts. Remember collision theory? Frequency factor, collision, and I've talked about proper orientation. That's all wrapped up in here. So next week, we're going to discuss first this, then this, in terms of how a chemical reaction progresses, and this thing here that we've been talking about, how this actually plays a role, assuming all of these things are constant. The main thing that's going to be constant, these things should be constant, this is going to be constant based on the temperature. So we're going to look at when you increase the temperature, what should happen to this piece, and therefore K, and if you decrease temperature, what should happen to this thing, and therefore K. Should that cause the rate to go up or down? The higher the K, the rate goes up.
Get your shape?
The lower the K, the rate goes down. And those are the dynamics that I want you to think about, and then I'll see you next Tuesday. So have a good weekend.
I need to read something and type it up really quick before class starts.
Fairly simple. I mean, what she's requesting?
Okay, see you, Janice.
I mean, I don't think there's a right or wrong way of reading it.
Right.
It's just like read and see, tell me if you understood. You can come up with anything and then later
A
on
summary
change
and then your analysis.
analysis. Besides summary?
Right, like the summary of it, and then yeah, what do you think? What are your thoughts about it?
Done?
Thank you, Maria.
Huh?
Thank you.